Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper data structures. In this module, we will be talking about a very important graph algorithm called the minimum spanning trees, and in this module, we will be discussing one of the minimum spanning trees algorithm, which is the Trees-Kruskal algorithm. So, these are the people responsible for the creation of this particular module, and the learning objectives of this particular module are to understand in detail the Trees-Kruskal algorithm to find minimum spanning trees, to discuss the implementation issues associated with the Trees-Kruskal algorithm, and to understand Trees-Kruskal algorithm through a walkthrough example. So, the keywords associated with this module are minimum spanning tree, greedy algorithm and disjoint sets. So, we will see how these disjoint sets are used to implement the Trees-Kruskal algorithm. Now, before we start off, let us just recap what is the meaning of spanning trees and minimum spanning trees. So, when a graph G is connected, a depth first or breadth first search starting in any vertex in that particular graph will visit all the vertices of G, that is a normal search or traversal. Now, a spanning tree is any tree that consists solely of the edges in G, it will consist only of the edges and includes all the vertices. Why we are telling this is, when we are talking about a depth first or a breadth first search, it is not necessary that the edges are in that depth first tree as it is called, or the breadth first tree as it is called, consists only of edges in the graph. It can consist of other edges, but in a spanning tree the definition is such that it consists only of the edges of G, and but it should include all the vertices of G. So, the edges of G are nothing but tree edges and non-tree edges. So, where T is the set of edges used during search and N is the set of remaining edges. So, basically when you talk about edges, you will talk about two types of edges, that is tree edges and non-tree edges. So, the edges in the graph are the edges in G. Now, the minimum spanning tree, that is the spanning tree. The minimum spanning tree for a given graph is a spanning tree of minimum cost for that graph. So, the minimum spanning tree, as we told, we are also looking at the weight or the distance associated with the edge, and we are trying to, or the cost associated with each edge, and we are trying to find the minimum cost, okay, spanning tree. So, before we go further, let us discuss what is the meaning of greedy algorithm, because the Trees-Kruskal algorithm is based on greedy heuristics. So, one of the assumptions that we are making in this particular graph based algorithm is a simplifying assumption that all edges cost C are distinct, that is all the costs are distinct, and then you have a cut property. If S is a subset of nodes and let E be the minimum cost edge with exactly one endpoint in S. So, you do not have too many endpoints, only one endpoint in S. So, S is a subset. If you take an edge E will be the minimum cost edge to one distinct point in S, then that particular minimum spanning tree will contain E. Then you have the cycle property, let C be any cycle and let F be the maximum cost edge belonging to C, then the MST will not contain F. So, that is how you remove the cycle. Now, look at the diagram given there. E, if you can look at this, you have S the subset, that is for the cut property, and E is an edge between one of the nodes and the remember it connects tree components. So, that edge connects one distinct node in S. So, that is the cut property, and here if you have such a cycle, then F is not, if it is a maximum cost edge, it is not in the MST. Now, let us look at greedy algorithm and the Trees-Kruskal algorithm. Now, Trees-Kruskal algorithm uses, why is it called a greedy algorithm? It is called a greedy algorithm because it always adds the cheapest edge that joins two disjoint components, locally the cheapest edge that joins disjoint components. That is why it is called a greedy algorithm. Okay. This is an example of a tree that we will be using. Now, we will first look at a generic algorithm for growing an MST. So, the generic algorithm goes like this. You have the graph G and the weights associated with the graph, and you have A which is initially empty. Now, while A does not form a spanning tree, what you will have to do is you will have to find an edge UV that is safe for A and add it to A, and then you return A. The set A is always a subset of some minimum spanning tree this property of it being a subset of some minimum spanning tree is called the invariant property. And then we said that you will find an edge that is safe for A, an edge u v is a safe edge for A if adding that edge to A does not destroy that invariant property that we spoke about just now. A safe edge is just the correct edge that we choose to add. Now, there are two algorithms that are very popular for this minimum spanning tree. They are the Kruskal and Prim's algorithms, and in this particular module we will be discussing the Kruskal algorithm, and in the next module we will be discussing the Prim algorithm. So, both algorithms are based on the generic algorithm. Now, the difference lies in a specific rule to determine this safe edge. So, set A is always a subset of the minimum spanning tree, which is the invariant property, and we want to find an edge that we can add to A. Now, in Kruskal's algorithm what we do, the set A is a forest and the safe edge added is always the least weight edge in the graph that connects the two disjoint components. So, what we do is you have a set A which is a forest, a lot of thing, and you add a safe edge that which is the least weight edge that connects the two distinct components. While in the Prim's algorithm what you have is a set A forms a single tree and the safe edge added is always the least weight edge, that is not changing, that connects the tree to a vertex not in the tree. So, the difference is in the approach. In one we are adding an edge, in one we are adding connecting the tree to a vertex that is not in the tree. So, that is the difference between the two. So, here we will be discussing the first algorithm, the Kruskal's algorithm. Now, the Kruskal's algorithm was created in 1957 by Joseph Kruskal, and now this is the crux of the algorithm. It finds a minimum spanning tree by taking the smallest weight in the graph and connecting two nodes, okay, and we keep on repeating until all nodes are connected to just one tree. Now, please note, when you are connecting to the smallest weight in the graph and connecting the two nodes, you may land up with disjoint components. Okay. So, this is done by creating a priority queue. So, that is to find out the smallest weight. We normally create a priority queue using weights as keys, and obviously the least weight should be in the front of the queue. So, the Kruskal's algorithm basically creates a forest of trees. Initially, the forest consists of n single node trees and no edges. So, basically the Kruskal's algorithm starts by creating a forest of trees. The forest of trees are nothing but all the vertices of the single node trees, all the vertices of the graph with no edges. That is the initial starting point. Now, at each step what we do is we add one edge, which is obviously the cheapest one, so that any of the two trees can be connected together. So, when you connect it, that becomes a new tree which of the forest, and so on. So, if it were to form a cycle, that is, that edge that we want to add forms a cycle, it would simply link two nodes that were already part of the single connected tree, so that this edge would not be needed. So, normally we do not consider a cycle. So, one of the properties that we have to check out is whether when you add an edge, a cycle is formed. If it is, you have to not add that edge. So, what are the steps of the Kruskal's algorithm? First, a forest is constructed with each node in a separate tree. The edges are placed in a priority queue. Now, and we keep on doing this until we have n minus 1 edges. What we do, we extract the cheapest edge from the queue. If it forms a cycle, if that edge forms a cycle with an already existing nodes in the tree, then we just reject it, else you add it to the forest. Now, adding it to the forest essentially means that you will be connecting two trees together. Remember, we started off with each node in a separate tree. So, you can imagine if you are adding a single edge, it just connects two trees of single node edges. Now, you have a tree with two nodes. Now, if you take the cheapest and connect it, it may connect with another single node or with this two node. So, else add it to the forest. Adding it to the forest will join any two trees. The trees may be single node, two node or three node, depending on which iteration of the Kruskal algorithm you are in. Every step therefore joins two trees in the forest together, so that at the end of the complete algorithm you will have only one tree. Okay, that is the basic of the Kruskal's algorithm. Now, why does this Kruskal algorithm work? The reason this works is that each added edge is a connection between two sets of vertices, because each tree is a set of vertices, and each added edge is a connection between two sets of vertices. And since we select the edge by in order of by weight, we are always selecting the minimum edge that connects two sets of vertices. So, that is the reason why this works. So, every time you are connecting minimum, so this will work. Now, cycle detection, now this is an important aspect of the Kruskal algorithm to keep track of disjoint sets. Initially each vertex is its own disjoint set. When you add an edge, you are actually unionizing two sets. A union cannot happen if two vertices are already in the same set. This would create a cycle. So, that is the idea. So, you keep track of the disjoint sets, then each vertex, initially of course, you know each vertex is in a disjoint set. Now, when you add an edge, you are trying to unionize the two sets. Okay, you add an edge and combine the nodes of the two sets together. Now, as per definition, union cannot happen if the two vertices are already in the same set, if that is so. So, that is how you find out there is a cycle. So, this union operation is an important operation of Kruskal. Now, let us look at the basics of the Kruskal algorithm. Now, you sort the edges in the increasing order. Initially A is empty, that is the final tree, while E is not empty, that there are still edges. Take an edge u v that is shortest in E and delete it from the list of edges. If u and v are in different components, then add u v to A. So, what we are doing is we start with A, and then while E is not empty, E is the edges of the graph. If that E is shortest, then you delete it from E, and if this u and v are in different components, then you add that u v to A. Each time a shortest always a shortest edge in E is considered. So, let us take an example here. We will first take a notional conceptual example, and then we will go a little bit into detail. So, now first step is you list the edges in order of size. So, here you have E D is the first edge 2, then you have A B 3, then you have A E 4, you have 2 with 4. So, A E 4 and C D 4, then you have B C 5, then you have E F which is 5 again. So, you have 2 5s, then you have C F as 6, then A F as 7, this is A F as 7, and then B F as 8, and you have 2 8s, and D F as 8. We have just taken it such that the lower alphabet is always at the end, because it is an undirected graph. Now, this is the first step. Now, what you have to do is you select the shortest edge in the network, which is E D 2. So, that is the first edge you will select. You remember, we have to find the minimum spanning tree. Now, the next step is you have to connect the next shortest, which is A B 3. Now, you can see that you can connect A B, because A and B do not have form a cycle with E and D. So, it is okay. You will see that you have two disjoint components, E D is one edge and A B is another edge. So, that is the next step. Next you have 3. Now, you could have, and the next you have to select is 4, which is at the front of the priority queue, as you remember. Now, C D you can do or A E you can do, any one is okay. So, here C D 4 is the one we select. You could have selected A E 4, that is okay. So, the order will be slightly different in how the edges are formed, how the minimum spanning tree is formed. So, you could have formed that. So, you have C D 4. Now, the next is A E. So, you form A E. So, you could have had A E 4 and C D 4 also, fine. Now, the next is 5. Now, if you choose B C, what will happen? It will form a cycle. So, you have to disregard it. The next is E F. So, E F is 5 and it is okay, it does not form a cycle. So, B C forms a cycle. So, ignore it, then you have E F. Now, the next one is 6. So, you have C F 6, it forms a cycle. So, you cannot have that. Then A F 7 also forms a cycle, you cannot have that. So, E F is 5. And so, you do not actually have to go further than this, because remember, by definition of the minimum spanning tree, your only condition is that all the vertices have to be in the minimum spanning tree. According to us, we have 6 vertices A, B, C, D, E, F, and all the 6 have been forms part of the minimum spanning tree. So, we do not actually have to consider 6, 7 and 8. Okay. So, once you have considered all the vertices, you can stop the algorithm, you do not have to look for the cycle. and you will see that the total weight of this particular spanning tree, minimum spanning tree, is 18. This will not differ, only the order. Here you have ED, AB, CD, AE and EF. You could have also had ED, AB, AE, CD and EF. Those, that is also a minimum spanning tree. Now, Kruskal's algorithm basic is that it always works with edges rather than nodes. So, there are two steps: sort the edges by increasing edge weight and select the first edge that do not form a, you keep selecting the edges that do not form a cycle. So, the only condition is select the minimum edge, see whether it forms a cycle with an existing minimum spanning tree. If not, you add it. Now, so again we will just look at this particular example and we will go in detail considering the data structure also. So, here you have a undirected weighted graph and it has A, B, C, D, E, F, G, H. So, 8 nodes. So, our spanning tree must consist of these 8 nodes. Now, what you first do is you sort the edges by increasing edge weight. So, here you have the edges and the weights. So, DE is the minimum edge, DG is the next one with 2, EG is 3, CD is 3, GH is 3 and CF is 3. Here you have 4 edges having the same weight 3, and you have BC, BE, BF and BH, all 4 again having the weight, edge weight as equal to 4, AH 5, DF 6, AB 8 and AF 10. So, this is the complete graph. This is just a graph representation. Only thing we have done is we have ordered in increasing order of edge weights. That is the only thing we have done. It is only a list of or a list of edges. Now, you have to select the first edge which do not generate a cycle. Here it is trivial. So, we first select DE, there is no question about it, that is the minimum cost edge. So, we select that. Okay. Next, we have to select the next one which is DG. DG is fine because it does not form a cycle. So, we select DG. Next, you have to select the next minimum. Now, you can select EG, CD, GH, CF, any of that is fine. So, EG can you select? You cannot select EG because it forms a cycle. You can select CD, fine. You can select GH, that is also fine. You can select CF, yes. So, we choose to select EG is not possible as I already told you, because if you select EG it becomes a cycle. So, the next one that we select is CD in the order in which you have put it. It is not necessary, you could have selected GH or CF if it does not form a cycle. So, you have selected CD. Now, 4 nodes have been taken care of, remember that also. Now, next is GH. So, that you can select because that does not form a cycle. So, you select that, it does not generate a cycle. Now, you are finished with 5 nodes. Next, you have CF. CF is also fine, does not form a cycle. So, that is okay. So, now you have BC. Now, if you put BC, it does not form a cycle. So, that is also fine. Next, you have BE. BE forms a cycle, right. Then you have BF. BF forms a cycle. So, you cannot have that. BH forms a cycle, right, you cannot have that. Then you have AH. AH does not form a cycle. So, you have that. After that, you can conclude the algorithm because you have to select only V minus 1 edges, right. Why V minus 1 edges? V is the total number of vertices. So, the number of edges that you have to consider is V minus 1. So, suppose you have 8, you have 7 edges. If you look at this, you have 1, 2, 3, 4, 5, 6, 7 edges you have to connect. So, once you connect the 7 edges, everything is over. You would not have selected duplicate vertices because of the definition that we have given. We said that no cycles are allowed. So, this is the basic algorithm, and so we do not have to consider the edges DF, AB, AF as I already told you, because we have considered all the vertices already, and as you can see, after removing the unnecessary edges, this is the minimum spanning tree, and the total weight of this minimum spanning tree, cost or weight or whatever you want to say, here its cost is 21. Okay. Now, the details is, now let us go a little bit into the details of the algorithm. Now, the MST Kruskal consists of the graph and the weight and A, this we have seen before. Now, for each vertex V in V of G, that is for every vertex in G, you have to make a set. Sort the edges of E by E, that is the edges, by non decreasing weight. For each edge that you have in that list in order of non decreasing weight, find if find set U not equal to find set V. That means they should not contain common nodes. If they contain, you cannot join them. Then you take the origin A and add this edge to that. So, that is you are doing a union of UV, that is you are taking two sets and trying to join them. Why I am discussing this here is, this is important because this is the property that makes you make sure that cycles are not formed. Okay. So, what you have to do is, as long as the sets are not the same, you add it and then you have to merge the two sets or disjoint sets such that you can form an union. That means there should not be common sets. Okay. Now, to implement this algorithm, let us look at the data structure considerations. So, to implement this algorithm, you need a way of representing sets. After all, the nodes and the edges together form sets. Now, to find which set a vertex is in, now you have an edge only. Now, when you have an edge, you have to find out the vertex comes in which set. Okay. When an edge is being considered for the minimum spanning tree, we must find which sets the edge vertices belong to. So, you have to find out, you have selected an edge, you have to find, like for example, you have selected A B means, you have to find where A is, which set A belongs to and which set B belongs to. So, you need a find set operation to find this set. So, what is the operation we need? Given a vertex, we want to find in which set it belongs to. So, that is a set operation that we want. The next set operation that we want is to get the union of two sets. If a vertex sets are disjoint, the edge is added to the MST and the union of the two sets is obtained. So, a union operation is also needed. Now, the problem is testing that an edge. The problem with Kruskal algorithm is, we want to test whether an edge creates a cycle. If you want to test that operation is very slow in using normal data structures. So, you need a data structure which supports these operations, and those that particular operation that you need to support is the union find data structure, which the union operation and the find operation. So, two standard implementation for such kind of union find data structure is the disjoint set linked list or the disjoint set trees. So, those are two ways in which this is implemented. Now, let us look at what do we mean by disjoint sets and then see what are the operations. Now, keep a collection of sets S1, S2 to Sk. Now, each set Si will have a set of list of vertices are associated with it. For example, S1 is a set that could contain V1, V2 and V8. Now, there are three operations that are necessary. One is to make set S creates a new set whose only member is X. Okay. So, creates a new set whose only member is X. Now, union XY unites the sets that contain X and Y, say Sx and Xy, those are the two sets, into a new set, that is the union of the two sets. Okay. So, this is how union is done. You have a set Sx and you have a set Xy, and you want to unite these two sets, then you form a new set which is the union of these two sets. Then you have a new operation which is very important, is find set X, that is it will return a pointer to the representative of the set containing X. So, suppose S2 contains that particular node X, then it will return S2. So, each of these operations, make set, creating a new set, unionizing two sets that contain X and Y, and find set X, finding which set X belongs to. Each operation takes of the order of log n. Now, if you look at the analysis of the Kruskal algorithm, the running time of the order of E log V, where E is the number of edges of the graph and V is the number of vertices. Now, it usually only has to check a small fraction of the edges, but in some cases, for example, if there is a vertex connected to the graph by only one edge and it was the longest edge, it would have to check all the edges, because that is can you understand what I am saying? That is you want to add a vertex, but that vertex comes at the end of the list. I mean that there is only one edge which you need, but that is not the minimum edge. So, you will have to check the whole list. Now, we have taken only 8 vertices. In real life problems, this set could be quite huge, the number of nodes. For example, you just take, you want to find the flight schedule for all the cities, you could have hundreds of cities and more than that connections. So, this algorithm will work best if the number of edges that you have between the given vertices is a minimum. Okay. So, in this particular algorithm, we explained in detail the Kruskal's algorithm to find minimum spanning trees. The crux of the algorithm was its implementation, because what we wanted to find was, we do not add an edge to connect two disjoint subsets if adding that edge will create a cycle. Okay. So, that was the basis. Now, to implement that, you can implement that using any data structure, but it is a complex operation, it takes a lot of time. So, you need a disjoint set operation, which has basically a union operation. You need a make set, you need also this find set, because find set, see, remember, in your algorithm what is given to you is only a list of edges, you do not know where it belongs to. So, given that edge, suppose EF, then you have to find E belongs to what set and F belongs to what set. So, explicitly in the walkthrough we did not show the two sets. Okay. The two sets are the sets, sometimes everything, in most of that except in the first where you have two disjoint sets, most of the time the set is thing. So, the set, everything forms a set, and you have one edge, that edge connects to one of this. Remember, the invariant property is also there. Now, we discussed the implementation issue associated with the Kruskal's algorithm. We discussed a new data structure called union find data structure, which is nothing but a disjoint set data structure that is implemented using disjoint set. We needed the following abstract operation, I mean ADT operations or operations with that particular data structure, where we wanted make set, that is create a new set with a node. Okay. Then we wanted union of union x y. So, you have an edge connecting x and y, you have to find the two subsets, say S of x and S of y, and then you have to join the two subsets. You have to join, not merge alone, you have to union these. That means, you can union these two only if they do not contain the same nodes. Okay. And we also illustrated the Kruskal's algorithm through a walkthrough example, where we use the data structure of a priority queue in non increasing order of edges, because every time from the front of the priority queue we would take the edge which has the least weight, and we will see whether adding this edge would form a cycle. For that purpose only we use this union operation. Okay. Because a node by itself, remember we started off by saying all the nodes by themselves form sets, singleton sets. After that we keep joining. Okay. So, this is the algorithm that we are talking about, and in the next module we will be discussing algorithm called the prim algorithm, which is for the same purpose, to find the minimum spanning tree. Now, do not think just because you have two different algorithms, the minimum spanning tree weight towards summation of the weight is going to be different. No, the basic difference between the two algorithms is that the way in which here we add an edge, in that we add a vertex to the set. So, that is the difference between the two algorithms, the way it is done is different. Here remember Kruskal's needed a specialized data structure called union find to implement this effectively, while prims does not need that. Prims does not use the disjoint union find data structure. So, with that we will finish.